Bismillah ar-Rahman ar-Rahim. So last time we started to talk about the different components of end-to-end delay. And we have mentioned the 4 components of delay, which is the processing delay, the transmission delay, the propagation delay, and the queuing delay. And we said that the trickiest one is actually the queuing delay because it's based on the statistical information in the network, and that's why there's no particular closed form equation that we can use to calculate the queuing delay. It's based on the arrival statistics of the aggregate packets to the queue of the router, and based on that, the wait time inside the queue is what we call the queuing delay. We also talked about packet loss, and we mentioned the different situation where there is packet loss. If there is any traffic jam on the router queue and the queue is full, then we have packet loss, and we have discussed this. Today, inshallah, we're going to talk about throughput. And as we are all familiar with the throughput talks about the rate in terms of bits per second that describes the actual bits that we can transfer from one end to another. The interesting thing about the throughput is that the throughput is a bottleneck based, which means that if we have an end-to-end, if we have 2 nodes end-to-end that are trying to communicate, in between these 2 nodes we have routers, we have switches, we have so and so, right? So and between these routers or network devices we have cables or links or wireless or something like this. So what is the average throughput end-to-end compared to the throughput on each link? That's what we want to discuss today. So first of all, we know that throughput can be measured instantaneously. Instantaneously, it's the rate at a given point in time. It's the rate that a sender can send to a remote receiver at any point in time. It's instantaneous, which means that if we want to calculate it, for example, using for simulation or using MATLAB or something, what happens is that we can have a very, very short window of time, let's say like 1 second. And we calculate at the receiver the amount of bits that we have received during this 1 second. And this we can call the instantaneous delay. Average delay, on the other side, talks about the average between all the instantaneous delays across a very long time. So, for example, so instantaneously, the rate in 1 second looks like this, and then it goes up, and then it goes down, and then it goes up, and then it goes down, and so on. So the average delay, the average throughput talks about the average value amongst this. And the way that we calculate this using MATLAB or something is that we consider the entire simulation time as the window of time, and we calculate the amount of bits that we receive during this entire simulation time, and this would be the average throughput. So we don't care about, so in instantaneous delay we take like a very short window of time, okay? Versus for average delay we take this entire duration of time as the and for each window what happens is that you count the number of bits that you receive at the receiver. You count the number of bits, and then this number of bits you divide it by the actual time, and this would be the average throughput during that period of time. So
instantaneous means the peak. We can say peak or trough.
No, instantaneous, no, not the peak. Instantaneous is different from the peak. This is the peak. Okay? At this time, this is the instantaneous rate. Okay? The peak means that during this entire window, what is the maximum throughput? So this is the maximum throughput, or this is the peak. We can consider this a peak, okay? And this is a peak. So these are peaks, in which case you have up and down. So this is the peak, okay? This is probably the maximum throughput, and so on. But the average is E. So you have different parameters to describe the throughput with respect to time. Another very important thing to notice here is that, okay, so when a server tries to send to a client or a sender and the receiver, in between the sender and receiver, you have a thickness of a pipe, and in between these two, there is like a network device. So, for example, here, there could be a router here, okay? So this is a link, and this is another link. So this could be like 1 megabits per second, and this could be 10 megabits per second Ethernet. Of course, this is the theoretical rate, but what you achieve here, for example, is like, let's say, 700K. And here, like, for example, maybe the rate would be, or the actual rate that you will get if you were to send from here to here, the actual rate maybe like 2 megabits per second or something. Okay? So if you send the traffic end to end, okay, what will be the throughput in that case, or the average throughput? So remember, the average throughput on this link is 700K. The average throughput on this link is around 2 megabits per second. So what do you think is the end-to-end average throughput? 700K. This is very important to notice here, because this is the one very important characteristics about the throughput, is that it's bottleneck based. Okay, so it's like you can think of it as a thickness of a pipe, and you're trying to feed some water flow. Okay, so if you have a thick pipe or a thin pipe, your limit will be the thinnest pipe in this whole pipeline, right? So the throughput is a bottleneck based. How about the delay, by the way, just as a question? Is the delay a bottleneck based or different?
Definitely based on the bottleneck.
So if we say that this link has an average delay of, let's say, 2 milliseconds, and this has an average delay of 4 milliseconds, what is the end-to-end delay? 6 milliseconds. 6 milliseconds. This is different from the throughput. So the throughput is bottleneck based. Delay is accumulative. Delay is why? Because when the packet goes from here to here, it will go through this delay and this delay and this. So the packet delay is accumulative in nature. However, throughput is bottleneck in nature. So if you have R1 and R2 and R1 less than R2, then the average throughput that you will get is R1. Okay? So this is very important to understand. So that's what this slide tries to explain. So the link on end-to-end path that contains the end-to-end throughput. So the one with the lowest rate constrains the end-to-end throughput that you can achieve. Okay, so that's why sometimes people complain. You say, like, I have a 10 megabit per second plan with Ooredoo, but I'm not getting any way close to 10 megabits per second. So what's going on? Well, what happens is that yes, your link to Ooredoo is 10 megabits per second, but in the core network, there is a bottleneck link that constrains your transmission. So the end-to-end throughput that you get is much less than 10 megabits per second. Why? Because there's a traffic jam in the core network. That's why at some point during the day, you may have very fast transmission, but at another time, you have very slow transmission. So why is this? Because the traffic jam goes up and down, and it's based on thousands of people are trying to consume the resources from the core network. So it depends on the statistical load on the network at any point in time. You can get high or low throughput. Okay, so this is very important to notice. So this link, for example, we're trying to calculate the rate per end-to-end connection. So if we assume that we have all these end-to-end links, they share one link in the core network. Okay. So what is the average throughput per end-to-end link or end-to-end connection? Sorry. Okay. So assuming that you have 10 different end-to-end connections, if all these connections are sharing this link, usually the sharing, the router will try to be as fair as possible for all the links, except if we are doing any kind of quality of service, which, as we discussed before, is all about discriminating between these connections. Assuming that there is no specific quality of service requirements, in which case the bandwidth per link here at this level, okay, for each connection it will be R over 10. Okay? So then the end-to-end throughput will be the minimum of RS or R over 10 or RC. So that's what this tries to explain here. Right? مفهوم دي؟ So here, from this link point of view, the average rate for each of the 10 connections is R over 10. Okay? And since we have 3 links for each connection, so the minimum of all these throughputs will dictate the amount of throughput that you can get, because, as we said before, throughput is bottleneck based. Right? So this is the average throughput per connection for this example. Okay? Assuming, of course, that the bandwidth at the core network link is shared fairly. Okay? Because this is not always. Okay, so we covered this topic. So we talked about packet delay and packet loss and packet throughput. We talked about circuit switching and packet switching and the difference between them. The last topic in this, which is kind of covered here for completeness, which is the protocol layers. As we all know, the layered model is a very important concept in networking. And because of the fact that the network function is really complex, because of the fact that we have different types of network devices, and we talk about transmission of information from the level of high-level data all the way into transmitting analog signals on different types of medium, whether it's cable, UTP, or fiber optic, in which case we talk about light signal or optical signal, or we talk about microwave signal in the case of wireless. So with that said, the network function itself is really complex, and one way of approaching this complexity is by using the layered model concept. Okay, the layered model concept. So to understand this, there is an analogy which is explained in the textbook about if you go on a trip to the airport, to an airplane, and so on. So you start from, first you have to log online and buy your ticket, and then you have to go to the airport. So you check in your baggage, you have to go to the gates in order to take your plane, and so on. So that's the same approach. So you can think of all these different levels or different stages during your trip as a type of layers. Okay, so and then when you go to the airplane, then you have to go on an airplane, which means that you are essentially a packet going on the network. Then you can flow from one city to another until you arrive to the airport on the other side. Once you get down, then you go up, you go to the runway and so on until you reach to the ticketing if you need to complain about anything or something. But it's the same levels. You have to do it the other way around once you arrive. So it's as if you are a packet and you go through all these levels and all these stages from at the sender side and at the arrival stage. So this concept of layered model is very, very important, especially for representing network functions. The first organization that did this is حد عارف؟ the first organization that kind of laid out this layered approach for describing network function. What was it? OSI, the ISO has actually developed the OSI reference model. The OSI reference model defines 7 layers, okay, for the network function. From the application layer, then presentation layer, session layer, network layer, and so on, all the way to the physical layer. They have defined the high-level function for each layer, and they have left it completely to the developers to develop their own protocols, whether using this layered approach or using any other approach. And what happened is that the most common model that is used by the internet, which is the TCP/IP model. The TCP/IP model kind of groups some of these layers together. So, for example, the application layer, session layer, and the presentation layer is kind of grouped into what we call application layer. So there is no 7 layers in the internet model. We have only application and then transport, network, and then data link and physical layer. Or sometimes they group the data link and the physical layer into what we call network access layer. Okay, so they've kind of grouped some layers together. So those are, but in any case, the layered approach itself is very key and is very important, and people agree that it's the best way to approach and describe the functionality of inside the network. So why is this? Why people thought about it this way? Well, there's one very important factor is that because whenever you approach any system that it's complex in nature, you need to break down the functionality into a more structured, sub-functions in order to be able to implement each sub-function efficiently, right? And that's what the layered model does. But we could do this. We could do the network function into sub-functions and so on. So why exactly the layered model? The different vendors, they have actually had some discussions, and they have came up with this layered model as a good approach. Why? Because layers, they tend to be very much isolated from each other. Okay? So in other words, if you make some changes in one layer, it does not affect the changes in another layer. So for example, in the transport layer, I can use UDP or TCP, and it's totally transparent to the network layer. So if I change the implementation of TCP, do I have to change the implementation of IP? No. You can change the implementation of TCP, and it's totally isolated from IP. So I don't have to provide any modification. So if you make any change in any layer, it does not propagate all the way down. So this is a very important concept because then it fosters the competition between the different vendors. And that's why nowadays you see that, Cisco, for example, Cisco, as large scale as it is, they never work on anything related to application layer or physical. They focus on network layer. Their operating system really focuses on network layer issues, right? Microsoft, they work on application layer and transport layer. They never work on physical layer, for example. They don't care about this, except for iPhone and other things. But in many cases, they use some existing IPs to implement all the lower layer stuff. So this isolation between the layers allows the different vendors to focus on one layer and provide and produce many contributions into this layer, in which case it fosters innovation. So you can innovate in each layer without affecting all the other vendors. So as long as you comply with a particular protocol in this layer, you are perfectly sure that your product will be able to communicate with another product. Like, for example, Windows can talk easily to Linux, right? So you can communicate between a Windows box and Linux box. There's no issue with that. Why? Because here is TCP and here is TCP. Even if you change TCP here and change TCP here, they can talk to each other. So the protocol in the same layer, as long as it complies with the standard, you can talk with any other vendor. So that's why we can use D-Link or Linksys routers, and there's no issue with anything. So you can take away your router at home, you can plug in a Linksys router, and there's no issue with the network. So it's still Wi-Fi, still, I don't have to change my devices, I don't have to do anything, right? So this really fosters innovation and allows vendors to focus in one particular layer without affecting the changes in any other layer. So this layered model is really important, and that's why the ISO, they have come up with what we call the OSI, or Open System Interconnection Reference Model, which first described the network function into 7 layers. And these are the different reasons, as we have talked about. Okay, so this is a very important question and interesting question. Is there any drawback to the layered model? Until very recently, we did not see anything, we did not see any issue with the layered model until we started to work heavily on wireless devices. Since then, we started to see some issues with the layered model that has to do with the fact that any layer would need some information from the other layer, especially when it comes to wireless, and I'll talk about why. There are so many scenarios, especially in wireless environments, that kind of, forces you, or at least encourages you, to get some information from other layers in order to perform your functionality more efficiently. And that kind of violates the isolation between the layers. So the layered model, as I said, one important characteristic is that there should be some isolation between these layers, so that any change here would not affect the change here. And that was really very nice, very novel idea, and everyone was happy about it. With wireless, for example, one scenario that we just talked about, if TCP, for example, has some information about the channel state, TCP would work a lot more efficiently than it does now. But in many cases, it cannot. Why? Because of the isolation between the layers. So if TCP knows that now there is a packet drop because the channel is faded, where do I get such information? From the lower layer, right? From the physical layer and from the data link layer. So if I know that this packet drop is because of the fact that the channel is faded, then I can work much more efficiently. Why? Because TCP uses, as we will see later, uses the drop in the packet rate, or in the transmission rate, exponential drop once it finds any packet drop. They call this congestion control. So for congestion control, TCP drops the packet rate instantaneously by half. Okay? Although this effect, if the packet drop is because of the channel state, this effect is not more than like 1 or 2 milliseconds. It's an instantaneous fading in the channel that should not affect the router queue, for example. But TCP does not distinguish. TCP will say, oh, okay, there is a packet drop. Okay, so there is a traffic jam and the router queue is full. What do I do in order to clear the router queue? I have to slow down. When I slow down, okay, it's like I got into the the bank, and I close the door. I say, close the door. I cannot accommodate any more packets into the network, and then I restrict the incoming, similar to what they do in highways. They get into the entrance and they say, oh, okay, this car goes here, this car goes here, this car goes here. So they kind of regulate the traffic that goes into the highway. Why? Because there is a traffic jam. And the only way to clear the queue or clear this traffic jam is to slow down for a period of time. And that's what TCP does. But unfortunately, in wireless, TCP has very, very bad performance because of this. Because in wireless, if every time you have packet drop, you have to drop by half, then in wireless it's very bad, right? Because every now and then you will drop by half immaturely, and then you start to go up again, and you spend a long time to try to use the link bandwidth efficiently. That's one example. You have tons of examples that they call this cross-layer approach. So by cross-layer, I mean in order to work in one layer efficiently, you need sometimes some information from lower layer or sometimes information from the upper layer. So this violates the layered model in terms of isolation between the layers. Okay?
But this does not depend on the layer itself. It depends on the protocol itself, TCP or UDP.
Yes. So well, actually,
not from the.
No, actually, this is not necessarily protocol related. This is related to interaction between different protocols and different layers. So if for example, TCP as a protocol has one parameter, packet drop, okay? It's like packet drop is just a counter, and it says, okay, this packet drop, I need to increment it by one. When there is a packet drop. But what is the type of this packet drop? Is it because of queue overflow in the router? Or is it because of channel fade, or because of what? So I need to kind of classify. Currently, TCP doesn't do that. Okay? And there are many people who worked on research to try to create some variations from TCP that really, it does exactly that. It classifies packet drop, whether it's because of this or this or this or this. And it lowers the transmission rate by half only if it's packet drop due to queue overflow. Or in some other situations, maybe it drops, but not by half, and so on. So it makes TCP more vigilant and more efficient, but this comes with the fact that it has to address, or it has to get some information from lower layers. Same thing applies across all the layers. So there is the paradigm of cross-layer approach, and cross-layer is a huge topic in networks, especially in wireless networks. In 3G, in 4G, in Wi-Fi, in Bluetooth, everywhere. Especially when we talk about wireless, cross-layer becomes, a very big issue. And actually, we have met the other day the VP for research from Cisco, and he identified cross-layer as one of the emerging paradigms that has huge amount of potential into enhancing the performance of the internet in the coming few decades, together with some other paradigms. But he identified cross-layer as one of the very important paradigms in networking.
Is it because of security reasons or not?
No, but sometimes even security, if you can perform security a lot more efficient if you get some information from the lower layers, especially in wireless. Also, especially in wireless. So wireless really has this feature that the channel dynamics is very fast, and also anything that you send in the wireless environment is broadcast in nature, so anyone can listen to it. So in many cases, by understanding the channel characteristics and the channel state at any point in time, this will allow any protocol in the higher layer to work a lot more efficiently. okay? And you can apply this to security, you can apply this to transport, to network routing and everything. So the concept of cross-layer is really very, very important. In any case, this is why I'm saying that in not 100% the layered model is the perfect way, but it's like the standard that we have been using since the internet was actually in life, in the picture. And I don't think it will vanish anytime soon. Even cross-layer, they have also proposed some techniques and some frameworks which allows the cross-layer to work within the layered model. So it's not to say that it's not possible, but it kind of, violates a little bit the isolation aspect of the layered model. In any case.
But one question, when a packet is dropped, then why this throughput is reduced to half?
That's how TCP works. Why? Because as we said before, if the queue is full, okay, if you get into the bank and the queue is full, what do? Anything that will come to the queue, it will get dropped, right? So the only way to resolve this issue is that you have to give some time to this queue to clear out before you accommodate more packets, right? That's exactly what TCP tries to do. So based on experiments, they said that, okay, so if there is any packet drop, we have to drop the traffic by half. Why? Because this will regulate the traffic going to the queue, which will allow the router to clear some packets from the queue and accommodate and then clearing the queue means I can start increase the rate. So what happens is that TCP, it drops by half and then it increases, very slightly and gradually. If there is any packet drop, it drops by half and then increases very gradually. So they call it gradual increase and exponential decrease. We'll study that in the next chapter. Okay. In any case, of course, the layered model, very important characteristic in the layered model is the encapsulation. And I assume that we all familiar with encapsulation. Encapsulation, you can think of it as a message. I put it in an envelope, and then I give it to the next layer. You put it in an envelope, and so on. So it's like packaging. You put something into a package, into a bigger package, and so on. And for each package, you have to label it that this is some kind of address. And as we know, in the message or the data from the application layer, it goes into the transport, and the PDU or the protocol data unit in the transport layer is called segment. So whenever we say the word segment, we know that we're talking in the transport layer. Whenever we say it's datagram or packet, we mean a network layer. If we say it's frame, we mean the data link layer and so on. So at every single layer in the transport layer, there is some type of addressing. In the network layer, there is another type of addressing. In the data link layer, there is a third type of addressing. So in the transport layer, we have the port address. In the packet, we have the IP address or network address. And in the data link layer, we have the physical address or the MAC address. So we have three levels of addresses. Each one is used for a certain thing, which we will talk about later. When I go through any network device, depending on the different levels in the network device, we have the switch. The switch is a layer 2 device, which means that you have physical and data link layer only in the switch, versus the router. The router is a network layer device, which means that you have three layers. So depending on what type of network device we go through, we go through all the layers and then we go down to the physical layer. And so this link and this link, they could be different, and that's why from one network device to another, or from one link to another, you have to regenerate the entire signal. So here I receive an analog signal converted into bits, and of course, in order for the switch to perform its function, it has to look up some kind of physical address. And in order for me to get the physical address from an analog signal. I have to get this analog signal, I have to decode it into bits, and then I have to form the frame, and then I have to read the physical address in order to be able to switch it to any of the output ports. And that's why we have to go up in the stack and so on. So depending on what type of network device, whether it's a switch or a router, I have to always go, decapsulation and then encapsulation, decapsulation and then encapsulation, and I keep doing this until I arrive to the destination. Okay.
So one question, sir. This after the physical, this binary data is converted into analog signals.
Yes, of course.
So it will not go
Yeah.
into the 1010 form. It will not go like this one. With current on off like this, it is not going. Or it means, suppose the frame, let us say 1010, it is the frame.
Right.
So when it goes to the physical, then it will not go as a 10.
No, of course. It goes as an analog signal. That's why the main functionality of the physical layer is encoding and signaling. And signaling, it converts the ones and zeros into analog signal. Whether it's electric signal in the case of copper cables, or light signals or optical signal for optical, and microwave signal for the case of wireless. And you have to perform modulation and so on and so forth. We did not.
Modulation and everything is done.
Well, it depends. Modulation for the case of wireless, or digital modulation for the case of also copper cable. You do some kind of PSK and QPSK or something like this.
Okay.
So all this is done at the physical layer. It's not part of the course.
There is one thing I didn't understand. Like after the frame, when you go to the physical layer,
Bits.
يعني zeros and ones?
Zeros and ones, bits. But then, in order for the bits to be transmitted over the medium, we convert the bits into an analog signal, electric signal. And there are some different schemes to do this. We will not cover it in this course, unfortunately. Because, again, this course covers the higher layers.
And the switch will receive the MAC address of the destination.
How? All these devices, they receive analog signals. At the physical layer, they receive analog signals. Then the analog signal will be converted into bits. The bits will be converted into frames, and from the frame, I get the physical address. Based on the physical address, I say, okay, I have to send it over this port, or this port, or this port, or this port. Okay? Same thing for the router. The router has to go through all the network layer. And then in the network layer, I use a different type of addressing, which is the IP address. And again, from the IP address, I look up the routing table, and then I say, it goes to this output router, or this output router, or this output router. Okay?
So it starts from the application and then it goes down?
Yes, so it starts from the application and then it goes down. But at the core network or at the network level, switch or router does not have any application layer or transport layer. They don't deal with the end-to-end application communication. As we will see in a minute, the transport layer is responsible for application-to-application communication. Okay? From one application to one. So from FTP client to FTP server, from web client to web server. The router doesn't care whether this is coming from web or this is coming from FTP. It doesn't care about this. All it cares about, based on the IP address, I will route it this way, or I'll route it this way. So it's similar to the fact that you're going into an intersection, and the intersection is like the router. So based on your final destination, you go into the intersection, and then you decide to go this direction or this direction or this direction. Based on what? Based on the final destination only. That's all. That's the only thing that the router uses. The IP address is the final destination, and it has this information in its own routing table that if I need to go to this final destination, the shortest direction is this or this or this or this. Okay, based on the final destination. It doesn't care whether this final destination is FTP or web or YouTube, or it doesn't care about this application at all.
One more question.
Mm-hmm.
This in router, there is another layer, is the network layer.
Right.
Network layer means here the signal is going up to the face of the datagram, correct?
Right.
So the address is not mentioned into the frame. This one, the link layer.
The address, there is another type of address in the data link.
It is normally kept into the frame, no? That it is source and this is the destination, and then afterwards bit packing and then CRC check and all this one.
Yes, but the address has a different meaning in the different layer. For example, you can you can understand, for example, the difference between the network layer address and the physical layer address using a very simple life, example. So the address in the network layer represents the location of that person. That this person is in this address, okay? This mail address, okay? So the IP address refers to the location of that person. And that's actually what the router does, because the IP address is actually divided into 4 pieces. And these different parts of the address gives you some indication about the location or the current location of that address, okay? So for example, if you as a person move from home to QU, your IP address will be different, right? And that's exactly what happens. The physical address is your name. Okay? Physical address is your name, which never changes. This is a MAC address. This is a physical address. It's hard-coded with you.
Okay.
Okay?
Yeah.
So if you move from QU to your home, your IP address will change, but you will not change, hopefully. So you can send, when you send a mail post, you say, I need to send it to person XYZ. This will never change, okay? At this location, that's the IP address. So only with those 2 pieces of information, you can get to the person exactly. So just the fact that the letter arrived to the house, it doesn't mean that it arrived to the person. Arrived to the house for us is that it came to the router which is connected to the network where this person is. So it came to the house, okay? So now I need to know which person in the house that I need to give this letter to. And there I have to use the physical address. So that's what the switch does. So I give it to a switch, and then the switch will say, okay, I need to send this to this particular physical address, which is the person. مفهوم كده؟
But the switch does not know about the final destination.
That's a very good question. I was waiting for someone to give me this. I was reluctant to get into this point because we did not describe the switch yet. But since you have, brought this issue.
I answer this one?
Okay, go ahead.
The reason is that, the switch is inside this one.
Inside the network.
Inside, and boundaries in the router. So router will decide that, okay, this is the switch, this is having, so I have to drive out here. So that's why switch is not having, doesn't bother about the address. Because it is connected, all the devices are connected into the switch.
Okay.
Whether here.
That's part of the answer. And the full answer is, inside the LAN, you need to know about the physical address of every single device in your LAN, within your LAN. Okay? Everyone needs to know the MAC address of all the devices connected. How do you know this? Well, usually you don't know the physical address, but you know the IP address, right? So if you need to communicate with an FTP server, let's say on the same LAN, you know the IP address of that machine for sure. But initially, you don't know the physical address. So how would you get the physical address? Well, we use a protocol called Address Resolution Protocol, or ARP. For Address Resolution Protocol, you say, okay, I need to know the physical address of that IP address. And you send this to all the machines on the LAN, and the one with this IP address will respond back with the MAC address. And actually, this is another security issue, because someone else might say, okay, I'm that person. Okay, that's source of attack. We know that. So, but normally, if there is no security issue, then the right person will respond back with the physical address. So any machine on the same LAN, you're supposed to know the physical. If you don't, then you can trigger ARP to give you the physical address for it. So when the router receives the packet, the router will say, what is the destination address? Well, yeah, the destination address on this LAN that I'm connected directly to it. So if the router doesn't know the physical address for this machine, it will trigger ARP to get the physical address for this machine, and it will send it with this physical address in the frame, which will then get to the switch, and then the switch will use the physical address to send it to the right machine. So within the LAN, you're supposed to know the physical address of all the machines in the LAN. If you don't, then you use ARP. So if I'm trying to send to an IP which is remote and it's not on the same LAN, what do? Do you have to know the physical address of the machines in China? No. No. So in that case, it's in a different LAN, in which case you give the packet to the default gateway, and the gateway will, so you specify the physical address of the default gateway. You give it to the default gateway, and the default gateway will send it all the way to China, and then the router in China will get the physical address for that. Okay? So only in your house you need to know the names of the people inside your house, but you're not required to know if you want to send it outside the house, you give it to the local post office, and they know how to deliver it. But you're not supposed to know the physical address of the machines outside your LAN. واضحة? Okay. All right. So this is the summary of this chapter. In this chapter, we talked about general, issues and concepts, and we talked about some basics like what is delay, what is throughput, what is bandwidth, what is. So it's just general terminology and things like that. We spent a long time really, but this hopefully will be a good foundation for us to launch the discussion for the chapters to come. I was debating with myself this morning because usually in previous course offerings, I did not cover the application layer at all. Because I thought there is nothing new really in the application layer. It's just a systematic description of how HTTP works, how Telnet works, what is the email architecture, and so on and so forth, which is, I did not find anything new really compared to any introduction to networks course before. However, I actually, I saw some interesting discussions about the difference between client server and PPP, and some like examples which can be motivating for the difference between P2P or peer-to-peer and client server, which we will summarize briefly, and then we'll get to the transport layer right away. So I will not cover any. So the application layer here will be a very short discussion. Okay, and then we'll get to transport layer, which I think is more relevant and interesting for many students. Okay, as I said, we'll cover chapter 2 just briefly. So the application layer, in the application layer, these are the topics that will not go through socket programming. We'll try to just address some issues related to client server versus peer-to-peer. Client server, there are some protocol descriptions for HTTP and Telnet, DNS, email, things like that. We're not going to go through all these details because I think they are covered in another course. And here we need to focus on more analytical problems, more interesting type of issues. So in client server paradigm, we kind of talked about the difference between client and server and peer-to-peer paradigm. And here we need to go into the depth of why we think the peer-to-peer, for example, is more scalable. What are the exact issues when it comes to client-server versus peer-to-peer? What is if peer-to-peer is actually that attractive, why we still use client and server, client-server model? Why it's still being used? What's good about client-server that makes people still attracted to use it? Can we analyze the performance of client-server and peer-to-peer and get some really quantitative results that will explain to us why peer-to-peer is good from certain angle, why client-server is kind of inefficient when it comes to scalability and so on. That's what we need to discuss. So we have some network apps or applications that use a network. This is not by any means an exhaustive list because the list is actually endless. But these applications, they have very diverse characteristics. And the more efficient, the more diverse the network can support in terms of characteristics for the applications, the more efficient we can tailor the resources of the network in order to address the characteristics of each of these applications and maximize the user experience. And that's our job. We're not going to go through all these applications. We need to work, or we need to discuss some architectures, some application level architectures. So usually we write programs, developers write programs that run on different end systems, or usually when we write programs as developers, we write the programs on a host, like FTP. We create or we develop an FTP client, an FTP server, we develop a web server. This is the maximum we can get to. We don't actually write code for core routers. Usually, we don't focus on. Cisco does that for us. So the developers in these types of companies, they focus on building or developing code for core networks to control and manage the operation of a router. Usually the application developer focus on developing end applications that is only used to compose the information and represent it in a good way to be transmitted over the network. That's our job as application developers. But at the end of the day, we don't really focus on writing code for the core network or for the router and so on. So these applications include like web server software that communicates to a web client, FTP server and FTP client, peer-to-peer like eMule or eDonkey or these kind of things. These applications, application developers, they usually write the code for. There's no need to write software for network core devices, usually, okay? So there is like principles for network applications, as I said, like discussion for HTTP, and which we will not get to. This application character or this application architecture is what we need to discuss in this chapter. So we need to discuss client-server versus peer-to-peer, and there is the hybrid model, okay? Because currently, as far as I know, there is no single pure peer-to-peer system on the internet. Okay, the most common one is the hybrid model. And we talked about this before. We talked about the fact that, yes, the content distribution is done as peer-to-peer. But at the end of the day, you have to have some server to maintain the directory and to maintain the location of where this content is. Okay, so this is the concept of hybrid of client-server and peer-to-peer. Okay. So client-server architecture talks about the fact that the server is always on. Okay, if the server is a fixed device and it provides a service, this service should be available 24/7, hopefully. Okay, so the server is always on. It cannot, go down, or it cannot be turned off most of the time, and we say that this is client server. No, the definition of a server is that the server is large-scale fixed device and it provides the service 24/7 or all the time. So it should be always on. It's permanent, and usually it has permanent IP address. Okay, that's why servers usually they get assigned a permanent IP address. They do not get DHCP or dynamic IP address based on moving from one location to another, because it's never moved from one location to another. It's always fixed and has a permanent IP address. So if one server is not enough, then you build what we call server farm, or maybe we can use cloud or something like this. The client on the other side, the client communicates to the server. The client itself doesn't have to be always on, right? I can turn off or turn on my client, but the client needs to be able to get a service from the server at any point in time, right? So whenever I open any application on my cell phone that communicates to an email server or web server or something, the server is always on, so I assume that whenever I need the service from this server, it's always on and it will get me this service, right? And I'm always the initiator for the communication. The server never initiates a communication with the client. The client is always the one that asks or initiates the communication to the server. It requests the service, and then the server will respond back. Okay? It may have a dynamic IP address, of course, so most of the clients, they use dynamic IP address through DHCP, and they do not communicate directly with each other. Usually, there is no client-to-client. Otherwise, this is another architecture, which is peer-to-peer. Right? So the clients do not communicate with each other. For peer-to-peer, all the applications are the same, same level. There is no server that's always on and we always request the service from this server. No, we all have same applications. We call them peers, and we can ask the service from any peer in the network. And depending on how many peers in the network at this point in time, I can ask any one of them, or I can ask multiple of them, or I can ask all of them to provide me the same service, which is which will be illustrated by some examples. The good thing about peer-to-peer compared to client-server is that, first of all, I don't have to have a server which is always on. Okay. Second of all, this increases the scalability, because if the server is down, everything is down, right? So the entire service is not available. So in peer-to-peer, the scalability is achieved by having multiple peers to provide the same service. So I can leverage the service from any one of them. I can leverage the service from all of them. Okay? So any of them can provide the service. Peers are intermittently connected. So you should not assume that the peer is always on, because it's not a server. If it's on, then you can connect to it. And sometimes you can connect to multiple peers at the same time. Okay? So this actually enhances the scalability. So instead of downloading a file from one single server, so you have only one connection with the server to download the file, I can actually create concurrent connections to 100 peers all at the same time to provide parts of this file. What will happen? I can download this file very fast. And this is exactly the concept of BitTorrent or this kind of peer-to-peer service. The problem now with this peer-to-peer, this is pure peer-to-peer architecture. The problem with this is that it's difficult, very difficult to manage. Why? Because if I need a service, if I need like one peer to provide me a file to download, okay, I don't know where this file is. So I don't really know which peer I should connect to. So if I don't have any information about where this file is, I have to connect to all these peers one by one, right? And each one I ask, or I send like a broadcast on the entire internet, which is usually not feasible, to ask all the peers. And I don't even know what these peers are. I don't even know who is currently available and who is currently not available. I don't know. I don't have this information. So, so somehow the management of all these peers and which peer is available at any point in time is really hard to manage. So we need to have someone with a global picture, okay? And that's why I have this hybrid.
Yes, but Doctor, with peer-to-peer, there is a problem that the security issue will increase, yes?
Why?
Because it is like the file on the peer device.
Okay.
So it might like, there is not like a server and it is protected from any like...
Okay. So, okay. We usually trust servers to provide this service because the server is maintained by a certain organization, and usually it's trustworthy, and you know when you connect to this server, you can get the service with a good level of trust. However, you can never trust all the peers on the internet. And that's why very likely when you connect to peers and you download a file from any peer-to-peer service, chances are there is very high possibility that it has virus. Very high possibility. And nowadays, the probability is like 80%. Because actually, many developers, they started to use this peer-to-peer concept to spread viruses in order to, I don't know, like use it as ransomwares or maybe get some information from your machine. And sometimes they use your machine to get the IP address of your machine, and sometimes use it for computation while you're not there, and you don't even feel it. So there are some different types of worms and viruses and so on and so forth, which can be achieved or attained using this peer-to-peer concept. So the peers are usually not trusted. In any case, so as we said, there is a need for us to have a global picture about who are the peers that are currently available, okay? Because if I need any service, I need to know who is available to provide this service, okay? And I need more detailed information about what type of service can each peer provide, what are the content that this peer has, and if I'm interested in any of this content, then I can communicate with this person. Or if multiple people has the same file, then I can communicate with all of them or any of them or something like this, okay? So as we can imagine, many of the current services on the internet, they use this type of service, the hybrid of client-server and peer-to-peer. Skype does that. Instant messaging, the messaging on Facebook, the messenger of Facebook, they use the same concept. There is always a directory server which has the global picture of who is available at any point in time. So when you start your peer, the peer has to authenticate first with the directory server. Okay? The directory server does not maintain any content. The directory server only maintains the state of the peers that are currently available and what type of content each peer has. Okay? Then, if I need to get a specific service from a certain peer, then I go to the directory server, get the information about this peer, and then I communicate directly with the peer as a peer-to-peer communication. Okay? I communicate directly to fetch the content or to get the service. Skype does that, instant messaging does that. Many of the services that we have, like BitTorrent is one of the very common examples for this type of hybrid architecture, as we will see.
BitTorrent also comes into this hyper...
Absolutely, yes. BitTorrent, Emu, because I need to download a file, right?
Correct.
Okay, so I need to know where this file is, who has it. So I need to go to the directory server, okay, to fetch who has this file at any point in time. This is the torrent. The torrent is the one that tells me who has this file at any point in time.
Give the path of that line.
Right. And then, knowing that this group of peers have this file, now you have the option to communicate with one of them, communicate with all of them, how, and so on. This is the BitTorrent protocol, which is very detailed. We'll talk about it briefly now. Okay. So, as I said, we'll not cover socket programming here. So the pure peer-to-peer, so this is, okay. So in terms of services which can be provided using the peer-to-peer, we can use this for file distribution, searching for information. If we need to, if we need specific type of information, we can search for information. But searching in a pure peer-to-peer architecture is kind of challenging, because then we have to do some exhaustive search. we cannot communicate with anyone who has a global picture, so your only chance is you have to go one by one. There's no other way. Okay? So this has a very big drawback. So instead, as we said, we have this hybrid approach, which uses directory server as well as peer-to-peer. So this example here explains this notion of file distribution. So if we have a server, okay, with a specific file, and this file needs to be downloaded by all these N clients. We have N clients who need to download this file. So using client-server approach, we need to distribute this file to all the clients, assuming that all of these clients, they will initiate the communication with the server and they ask the server to download this file. So now the server has N requests from these clients to distribute this file. So in order to understand the difference between client-server and peer-to-peer, we need to calculate the distribution time of this file to the N clients using the client-server model and using the peer-to-peer. Okay? As we can imagine, the scalability on the peer-to-peer side would lead to the fact that the distribution time would be less or more. The distribution time. The duration of distributing the file content in the case of peer-to-peer is less or more compared to the client-server.
Less.
Why? Why more?
Because it goes to each one.
For peer-to-peer?
Yeah, if we're not using hybrid.
If we're not using hybrid.
Yes.
No. Now we know hybrid will tell us the fact that this file exists for the peer-to-peer. Hybrid will only tell us that we need to distribute this file to these N clients. Okay? Or for client-server, these clients will request the file content from the server, so the server now needs to distribute this file to the N clients. Okay? The difference between client-server and peer-to-peer is as follows. The server, for the client-server, will have to be the only source of this file content to all the N clients. For the peer-to-peer, however, there is a file distribution scheme that can be used in order to break down the file into pieces and distribute all these pieces to all the N clients. Okay? So break down the big file into small pieces, and then these pieces will have to move to all the other N clients. So let's see what is the difference between the client-server and the peer-to-peer, and see how much distribution time we need for each case. So some terminology here, we need to know that for each client, you have an this is download speed, and this is upload speed. Okay? And here the server has an upload speed of US. So the US here is the upload speed for the server. Supposedly, of course, that US is more than all the UIs, right? US here is supposed to be very high compared to U1, U2, U3, and so on. Okay? And DIs as well. So the DI is the download speed. So typically the client would use some kind of ADSL. Okay? And ADSL is very low upload and faster download. We know it's asynchronous, right? So that's ADSL. But in any case, the US is usually more than all the UIs and possibly all the DIs. Okay? So simply for the case of client server, the only source for this file is the server. And this file will need to be distributed to all the nodes.
Same file to be all nodes.
Same, yeah, so it's always one to many. It always goes to from the server to all clients. Okay? So if I have n requests from these clients concurrently coming to the server, then the server will have to send the file content to all the n nodes. So I can select part of the file, send it to node 1, part of the file, send it to node 2, and then send it to node 3, send it to node 4, and so on, all the way to n. And then get the second part, send it here, 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 and so on. Okay? So now, in terms of distribution time, we need to calculate the distribution time.
Sigma di divided by n.
Yes, so basically, the time, if we assume that there is no bottleneck from the download speed of the client, okay, so we have basically n times f. So the file size is f.
Okay.
In terms of amount of information that we need to send is n times f, right? And this n times f, we need to send them to all the clients at the same time. Okay, all the clients at the same time. So basically, the distribution time, or the time that we take, is the amount of information divided by the speed of this link, right? So basically, this is supposed to be the distribution time. So the distribution time is NF divided by US. And this is supposed to go to all the clients. This is enough time to go to all the clients. Except that if one of the clients has a download speed which is really a bottleneck, in which case the rate, as we said, the speed on this connection, right, is defined by the bottleneck speed, right? So it's either the speed for this connection, for example, is defined by US or DI on any one of them. Okay? If there is one of them that's really a bottleneck, then the time to take to send to this client only is much higher than NF divided by US, which means that this guy is like a bottleneck. Okay? So in which case, the time taken to send to one of these peers or one of these clients is higher compared to NF divided by US.
I don't understand.
So, okay, so the amount of information that I'm trying to send is NF, right? Right?
It's fixed for all of them.
It's fixed for?
All of them.
Yes, I need, at the end of the distribution, I need to get F, which is the file size, to all the N clients, right? So I get N times F divided by US. This will give me the amount of time that I need to send this information to all the N clients, right? So this will be enough, but remember, I can send this to all of them at the same time. And this time is enough for me to send to all of them at the same time. Okay? Type.
But in this case, there shouldn't be no limitation from the client side.
Yes, that's assuming that the speed that I use to send, which is US, is actually absorbable by all these clients. Right? So if the download speed on all these clients,
Are equal.
not necessarily equal, but they are at least US or more or something like this, so that there is no bottleneck. Actually, the speed or DI should be more than or equal to US over N. to US over N. If this condition is fulfilled, because if I send NF with a speed of US, this means that on the average, each of the clients will get a rate of US divided by N, right? So if this rate is good enough for this client, which means that DI is more than US divided by 10, I will not have any bottleneck. Which means that whatever I send to any of the client, this client will absorb and will be able to consume this information without any issue.
What is bottleneck?
bottleneck معناها ايه؟ bottleneck معناها I'm sending with a high speed and then all of a sudden there is a, you know, the bottle, you know, the neck, the neck of the bottle. So you have like you have a amount, yes, and the neck of the bottle is restricting a specific flow to go out from the bottle. That's why we always call it a bottleneck.
I thought it was a scientific word, so I was like, what is this?
No, it's always a term that we use for the fact that you go from a high rate to a low rate. Okay? So if all the DIs or each DI is more than US over M, then any information that I will send to any of the clients, the client will be able to absorb with no problem because there's no bottleneck. But once the DI becomes less than US over N, this client will restrict a bottleneck, so I have to slow down. So that may actually cause more time for me to distribute this file to this particular client, right? So this client in that case will be a bottleneck and will increase the distribution time. So if all the clients can absorb, then that's fine. This is the amount of time that I need. NF over US. This is the time. Unless one of the clients has a DI which is a less than US over N, in which case this client will be a bottleneck and it will force the server to slow down. Okay? So in that case, for this particular client, the client that has DI, which is very low, the time taken to distribute to this file is F over DI for this particular file. Okay? All the clients that has DI less than US over N will cause this problem, will cause the server to slow down, right? So the most time amongst all these clients is the one with the minimum DI. This is the one that will be the bottleneck of the entire system. There could be more than one client, right? There could be more than one client. But I select the one with the minimum DI, and this will be the bottleneck of the entire system. And this is the one that I will spend most of the time to distribute the file content to this client. So this time will be F over minimum DI, and this will be the largest time, because minimum DI means that F over minimum DI is the largest time, right? So this time will happen to be more than the time that the server will spend to send to all the clients. And remember, DI here corresponds to US over N, right? Because it's less than DS over N. So in that case, this particular client will be the constraint for the distribution time. In that particular case, when DI is less than US over N. Okay? So basically, the total distribution time is the maximum of both. If all the DIs are more than US over N, then in that case, the distribution time is NF divided by US. Okay? If one of the DIs is less than US over N, so most probably this particular client will be a bottleneck, and the distribution time in that case will be f over this minimum di. This is for the case of client server. If you have any confusion about this, we need to clarify because the next is even darker than this. Go ahead.
If we have like a large number of ants,
Right.
consume more time for the file distribution, yes? Like it,
ما هو this is the time. NF divided by US. This is to send to all, right?
All, correct.
To all. Except if someone is restricting you down, if is slowing you down, in which case this will be the more dominant part. Okay. So this is for the client server case. So the distribution time is actually the maximum of those two quantities, even either NF divided by US or F divided by the minimum DI.
What was it?
Yeah, this is it. أنا عمال بقى عشان I do many marks and I cause some, so this is cleaner, huh? So this is the closed form equation. This is the minimum distribution time. So the minimum distribution time is the maximum of those two quantities. If the if all the DIs are more than US over N, in which case the server can send to all the clients and all the clients will be able to absorb that rate, in which case there's no bottleneck from the client point of view. Okay? Otherwise, if there is a bottleneck, this will be the dominant part. Okay? So this is for the case of client server. So remember that this is clearly linear in N.
Yes, depending on
And this clarifies the issue that client server is not scalable. So as N increases, the distribution time clearly increases, right? So this is the problem of client server. So imagine if you are distributing this file content to 1 million clients. So you see that the distribution time will increase linearly. Okay, so this seems to be, so that's why sometimes you connect on BitTorrent. I'm not sure if someone has tried it before. If you connect on BitTorrent or Emule or some of these services, they say sometimes server is full. Please look for another server, because each server has certain number of so any server on earth, even web servers sometimes, any server can handle a certain amount of calls or certain amount of requests and at one point. So so especially if we're talking about server distribution for a file content, so this server has certain capacity. So at the end, after maybe 100,000 users, 1 million users, the server may shut down or may go out of order. Okay, because the client-server approach is usually non-scalable for very large number of clients. Okay, or even if it can absorb or can accommodate 100,000 users, as you can see clearly, the distribution time will be very, very large. So if you are downloading a file from a FTP server using client-server approach, sometimes this file takes 1 minute, sometimes this file may take 1 hour, 2 hours, the same file. Why? It depends on how many people are concurrently downloading this particular file. Okay? So file distribution for the peer-to-peer. So here, the server, so assuming that the server is one of the peers, but it happens that the server is not a client server. The server is one of the peers. But this server or this peer happens to have the content of the file. And then all the other peers, they are requesting the content of this file. Okay? So at the end, what we need to do is to distribute the file content to all the client. The difference here is that clients are allowed to communicate with each other. In the client server, clients are not allowed to communicate with each other. Right? But here, clients can communicate directly with each other. So how can I leverage this to minimize the distribution time?
Distributing to all the clients.
What happens is that each peer, the peer who has the file content, will divide this file content into chunks, as we will see. And I can send one chunk to one peer. Now, we have two chunks on two peers.
The same information.
The same information. Those two chunks can, in parallel, go to another two peers. And in one iteration, we have the same file content on four peers. Those four peers will become information providers who can, in another iteration, send it to another four peers. Okay? So in other words, the server does not have to send the same content of the file n times. No. The server itself needs to send the file only once to any, because it divides the file into chunks, and it may send one chunk to one peer, one chunk to another, a second chunk to another peer, third chunk to a third peer, and so on.
But if you send like information and you divide it into chunks, but if you're sending each one a chunk, won't the information be lost? Like this has
Why?
one chunk. Or
No, Mona, it's not lost. We have different chunks at different peers. Each chunk is not usable on its own, right? We know that. But now we have distributed chunks on distributed peers. And now the clients can leverage the peer-to-peer communication to distribute each one who has a peer. He can provide it to another peer, and he can get, in return, another peer from the other peer. So in one iteration, we can exchange n by 2, for example, peers, can provide information to n by 2 peers, and at the same time, the other n by 2 peers can provide other pieces of the same file to the other n by 2 peers. In all of this in one iteration, and they can leverage remember here, by leveraging the peer-to-peer communication, I can leverage the speed of different links on the network. Right? So I'm not restricted that everything is sent from US by the rate of US. Now, I can leverage US, I can leverage U1, U2, U3. So all of them can be used concurrently at the same time. Right? Each of the clients will have different parts of the file, and they can upload it to others concurrently. Right? It's as if I have a system with a capacity US plus U1 plus U2 plus U3 plus U4. Right? So for different points throughout the time, I can have concurrent transmission. One chunk can be sent from the server. Another chunk concurrently at the same time will be sent from client 1 using rate U1, right? Another chunk can be sent from client 2 using U2, right? And so on. And this happens concurrently.
But this will not be the hybrid?
Hmm?
The hybrid,
No, forget about hybrid. This is content file distribution. The hybrid or not hybrid, the directory server will give us the information that this file exists on this particular peer, and we want to distribute it to these peers. We have passed this stage already. So now we are in the content distribution phase. And now we have a distribution, we have a scenario where we have one peer only, initially, with the file contents. And n other peers, they request this file content, but using the peer-to-peer communication, not using the client server. Okay? And why we want this scenario in particular to be able to compare it with the client server, because in the client server, this is exactly the scenario. We have the file content at the server, and we want to distribute it to end clients, right? Except the only difference here, or the main difference, which is, of course, fundamental difference, is the fact that peers are allowed to communicate with each other. In the client-server model, there is no such thing. Peers or clients cannot communicate with each other. They can only communicate with the server. For file content, for directory, for everything. Okay?
When the server sends a chunk, it has to be a full information, like the full file?
No, no. As we said, what happens is that the file content will be divided into small chunks. Let's say packets. The server will now send one packet to client 1, packet 2 to client 2, packet 3 to client 3, or can send it with any other sequence. It's totally free. But now the server is requested to send the file content only once. To who? We don't know. Okay? The file content, it will send it only once. And we assume that this one time will be enough. Why? Because we can leverage all the other clients, okay, through peer-to-peer communication to distribute the different chunks to each other without having to go through the server every time. Is that clear? We don't have, the clients do not have to go to the server every time to fetch any file content. The server will send it only once, and these different chunks will be existing at different peers. So now all these peers will become potential servers. All these peers will become potential servers. They can provide these different chunks to other peers. But from the server point of view, it needs to send it only once. So that's why, if we do this really carefully, and we send the first chunk to one user, the second chunk to second user, and so on and so forth, by the time, if we have everything great and everything works fine, perfect, by the time the server finishes sending one file content, all the different chunks will be distributed to all clients, to all peers. So this is one possible scenario. So the distribution time in that case is F over US. So no need for, so we send one chunk, now we have two peers who have this chunk. So the other peer will send this chunk to another peer, and so on. So by the time the server finishes sending the file content only once, this file content have been distributed to all, leveraging peer-to-peer communication directly. So this is the first scenario. Okay? Or maybe we have, again, the same scenario like last time. We do this, but there is a client that has a bottleneck, so same thing. This third scenario is the interesting one. We need to send the file content distribution n times, but leveraging not only the speed of the server. In that case, we are sending on n different connections in addition to the server connection. As I said, we are sending one chunk of data to one peer, and then this peer can send. So we can do that. Let's see. So this is the server, and this is one client, and this is another client, and so on. Okay. Now the server has this file in terms of chunks. Let's say 1, 2, 3, 4, 5, 6. So this file size is divided into 6 chunks. Okay? The file may send chunk 1 here. This is one time slot now. This is one packet transmission. Okay? The entire content still exists on the server. the server will send chunk 1 here, okay? In slot number 2, now, the server may send chunk 2 here, okay? And at the same time, this one will send chunk 1 here, okay? Those two actions happen in one transmission. So 2 sent here used which rate? Used the rate of the server, which is a US. So this transmission used US.
If US is
The rate for transmission from the server. If US is not, yeah, if DI is not, if DI is not a bottleneck.
yes.
Okay? And this one used اللي هو UI is the upload. U1 in that case, let's say. So those two transmissions happen with a rate of U1 plus US. Okay? So after you do this multiple times, you get to a state where you can send n concurrent transmissions with rate of US plus U1 plus U2 plus U3 all the way to the UN. So it's as if you are sending all the information that you are trying to send, which is n times f, right? So you want to send, at the end, you want to distribute how many chunks? N times f, remember. Okay, we need to send n times f chunks. But the difference here is that using the peer-to-peer, we can do some concurrent transmission, leveraging the peer-to-peer. So we're not restricted only with US. We can send with US plus U1 plus U2 plus U3 plus U4 all the way to UN. So it's as if we have a system with an aggregate capacity of U1 plus US plus U1 all the way to UN. So that's why we have this third term here is new, and it's very interesting.
This is dominating one.
Yeah, so any of these three is the dominating means that it's the maximum. Any of these, when it's the maximum, this is the minimum distribution time for this entire system. Okay? So again, if this is very low, then the dominant one may be this one. Which means that by the time the server will distribute the file content only once, all the other peers are very efficient in distributing this file chunks to all of them very, very fast. Which means that in that case, the UIs are very fast. They are all like more than US. So in which case, the US is actually more of the bottleneck. Okay? Or DIs is the bottleneck, similar to the scenario before. Or in that case, the aggregate capacity of all US plus all the U1s plus all the way to the UN is actually the bottleneck. Okay? So that's this is a very interesting scenario. So clearly now, when we look at this is not linear in n, right? So now, by looking at this equation, we can draw some very interesting conclusions. We can see that n disappeared. Well, you can tell me, oh, we have n here. Yeah, but remember, this n is divided by all the speeds of all the n. So here, if we assume that all the US's and UI's are the same, so you have here UI multiplied by n. So n will disappear, right? So n has disappeared from this equation. So this is a very interesting conclusion now, that no matter how you increase the number of peers, the system will still be scalable, and it does not care how many people are existing in the peer-to-peer network. It doesn't affect it. And this is a very fundamental characteristic for peer-to-peer architecture. This is the biggest benefit for peer-to-peer architecture. Why? Because of leveraging this peer-to-peer communication. Leveraging peer-to-peer communication allows the peers to concurrently utilize the network resources at the same time. Of course, from the network point of view, this will consume more resources. It's not a magic. At the end of the day, it's not a magic. We are still here consuming more network resources. But again, this assumes the fact that network resources are available and they are not actually used efficiently. So peer-to-peer architecture will allow you to use it efficiently in a more distributed fashion, rather than creating bottleneck by restricting all the communications to go into the server, in which case the server will form some kind of a bottleneck and will restrict the distribution time to be linear in N. Okay?
We asked a question at the beginning of this topic. You said that which one has a faster distribution rate?
Of course, peer-to-peer now has a...
Yeah.
So your answer was not right. So at least now you understand why we're saying that. And again, this is assuming that we leverage peer-to-peer communication, which allows us to support concurrent transmission between the peers at single point in time. Okay? For client server, we cannot do that. We always have to go through the server for everything.
And one more thing here is that in this case, server is not that much strong as
yeah, we don't have,
high
yes,
required.
we don't have to have a humongous server which is always on. Okay, that's not a restriction for peer-to-peer. We can leverage whatever resources and whatever speeds that these peers can provide us. And it depends on what type of connection each peer has. We'll talk about this. So now, we did mention if these UIs are very diverse and there is a huge gap between them. So actually this scenario is clean. It's actually straightforward compared to how complex this scenario really is. Because in reality, what happens is that these UIs are really diverse. There is a huge gap. One peer would have a leased line T1 connection with speed, 100 megabits per second. Another peer would have a dial-up connection with 100 kilobits per second. So how can we leverage this diversity in terms of speed? That's another issue. So here we're talking from the application level point of view. It's very abstract. We don't care what the network will give us, okay? All right, so this is how it looks like. So basically this is the distribution time. This is the minimum distribution time. And don't get confused that the minimum distribution time is formulated using the term maximum. Huh? We say this is the minimum because this is the lower bound. So all these terms that we talked about is the lower bound. But the actual thing might be more. Why?
Because maybe one of the...
Because of the throughput. Because you may send some chunks and it gets an error and you use TCP to do retransmission, right? So just the fact that we use US, this is US and UIs, and this is the average speed. But the actual speed may be higher, may be lower. Therefore, the distribution time is the minimum distribution time. And it's formulated in the maximum term, which means that the maximum of these quantities will represent the minimum or lower bound on the distribution time. So it's clearly linear in the case of client server, which is a O of n, basically. It's O of n. And in the client server, of course, it depends on which of the three quantities we talked about is the dominant. So it also increases as n increases, but at certain time it becomes almost stable. Okay, so regardless of n, it still gives you that more or less the same distribution time. Why? Because for client and server, each client is an overhead. Because it's a passive client. It does not provide a service. It's a consumer. So the more clients you get, the more overhead you have. In peer-to-peer, no. Each peer is actually a service provider. So it consumes a service and provides a service at the same time. And that's why we have this behavior. It stabilizes at a certain point. Okay? Okay, so any questions? Okay, so that's an interesting scenario that I thought we can discuss. It has some, analytical value and some, but when it comes to HTTP protocol and GET and POST, and this is a straightforward information that we are supposed to know already. So, okay, so in terms of file distribution, there is a practical peer-to-peer service which is called BitTorrent. So BitTorrent itself uses a slightly, a particular technique for peer-to-peer communication. So first, it talks about a tracker. A tracker is a designated, so as we said, you asked a question earlier about when actually someone requests a file or something, he gets into the system. So we need to know that this person is interested in this file content or something like this. So this information is maintained by what we call a tracker. A tracker is like a designated peer, which is stored in the torrent. Okay? This designated peer will maintain the information of all the peers that are interested in this torrent or this file. Okay? So when any peer comes into the picture with this torrent, the tracker will say, okay, this peer is now part of the group. This peer is now part of the group. And it forms, you can think of it as a multicast group, and anyone who is interested in this torrent will join this group. Okay, so now we have multiple groups, okay, multiple logical groups. Each group is interested in a torrent, or torrent corresponds to a file, a specific file content. So this group has to be managed and coordinated using one peer. Again, this concept of someone has to have the global picture. Okay? Someone has to maintain the global picture. Okay? So that's what we call a tracker. A tracker is one of the peers who's designated. Whoever is interested in this torrent, the tracker will say, okay, the group now has one more person. The group has one more person. So we form a logical group, which at some point it may grow large or it may be small, depending on how many people are interested in a particular file. So this is what we call a tracker.
The tracker is from Torrent itself? They put a designated.
Yes. So once you say, I'm interested in this torrent, right? I'm interested in this torrent, this will establish a connection to a tracker, which is a designated peer. Where do I know this? From the directory server. So the directory server will direct you to this group tracker, and the group tracker will say, okay, I now have one more person who is joining the group that are all interested in this file or in this torrent. So we form a logical group, okay, inside the big peer-to-peer network. This group is interested in a particular file.
And also the tracker, is it responsible also for each node, how many packets they receive or remaining to finish?
I don't think so. I don't think so. I will talk about the technique that BitTorrent uses in order to select which chunk it should download and which chunk it should give to other peers. So in other words, to answer your question, this is not centralized from the tracker. This is distributed from each peer, and we'll talk about that. Okay? So the tracker only maintains the connection or the IP addresses, basically. It only maintains the IP addresses
Informing the group.
of the group.
Yes.
And this group is interested in this file distribution. When I join this group, I come into a new group that, by the way, I come into the group and now I don't know which chunks of the file exists in which peer yet. Okay? Then, but at least I know who are the members of this group, right? So what I can do first is I can ask them, I can now ask them who has which chunks of this file. This is the protocol of the BitTorrent. This is what BitTorrent gives you in terms of application level protocol to first fetch which peer has which parts of the file. And now you need to decide two things. Which chunk I need to download from which peer. Okay? And another decision. Which chunk I should give to others, because remember, you are an information consumer and information provider at the same time. So you have a download decision and an upload decision. And it's not left, for BitTorrent. BitTorrent talks about a particular technique for how you can decide what to download and what to upload. It's not left sporadic. Why? Why? Because I need to make sure that there is no selfish behavior from some of these peers. Because you know what can kill this peer-to-peer approach? Is if some of these peers are selfish. Selfish means I need to get everything, I don't want to provide anything. يعني بالعربي كده لا يا حبيبي. It's a two-way street. Okay? So I need to be I need to be constructive. I need to be a good citizen in this group. And that's what BitTorrent forces you to do.
Yeah, to be generous. Yeah.
To be not necessarily generous, fair.
Fair.
I need to be fair. Okay, I take some chunks from people. I need to provide also. I need to be a good citizen in the group that I'm in. Okay, so BitTorrent provides certain techniques to avoid selfishness. This is not to say that once I get to this group, I'm not allowed to exit. No, I'm allowed to exit at any point, of course. But at least while I'm downloading the file, I cannot restrict to say, okay, I cannot provide any chunks to anyone. This is selfishness, and I need to be vigilant to this. I need to be a good person, or I need to be a good citizen. So BitTorrent basically provides a way to trade chunks in a positive manner. Okay? So the way it does that is that the file is usually divided into pieces. Each piece is like 256 kilobytes. Usually it's one packet basically. So each of these chunks could be in, actually 256 is a little bit high, maybe in multiple packets, maybe. Because the maximum packet for مثلا Ethernet, I know it's 1500 bytes. Yeah, 1500 bytes. Yeah, 1500 bytes. So it's much less than this. So each chunk is possibly few packets, not just one packet. Type peer joining a new torrent or a new group, and as we said, torrent is a group who are interested in one file. Initially, if I join, I have no chunks. So now I will accumulate these chunks over time. Registers with the tracker. Once I get in, I need to register with the tracker. So the tracker now maintains the group. In other words, maintains the IP address of all people in this group. So while downloading, peer uploads chunks to other peers. And at the same time, it downloads chunks from other peers. Once peer has the entire file content, if I have the entire file content, now I can selfishly exit the group. You are allowed. مفيش مشكلة. During the download, you have to be a good citizen. You have to be an information consumer at the same time information provider with the chunks that you already have. Okay? Even with a low speed, that's fine. Because the more you contribute to the group, the more the group will contribute to you. So the protocol manages this relationship. Okay? Okay, so there's pulling chunks and sending chunks. Pulling chunks is based that at any given time, different peers have different subsets of the file, chunks, okay? So periodically a peer, let's say Alice, asks each neighbor for the list of chunks that they have. So every now and then I ask which chunks each peer has. And now I have peer 1, for example, has chunk 1 and 3 and 5. Peer 2 has 2 and 6 and 10. Peer 3 has, and so on. So now I have this information. Okay? So which chunk I should download? BitTorrent, of course, they have done a lot of experiments. This does not come sporadic, by the way. They do some simulations and experiments, and they come up with a strategy that they think is good, and it provides some kind of a, and it provides, for example, they can use some optimization to minimize the distribution time. And they have found that for pulling chunks, each peer should be sensitive to the rarest chunks. In other words, if I know that chunk number X exists the fewest in fewest number of peers, okay, I should start with this. In pulling chunks, I need to know, for example, chunk number 10 exists with only one peer. Chunks number 11 like has 10 peers, or 10 peers has it. Then I should start with chunk number 10, rarest. Why? Bravo. To make more redundancy for this particular chunk, because chances are, what if this peer goes out from the group? Then none of the group peers have this chunk, and this is not a situation that we'd like to be in. So this is restricted by the BitTorrent protocol as part of becoming a positive citizen in this group. Okay. So the scheme for for selecting which chunk to download is based on the rarest first. So start with the one with the fewest number of occurrences and fetch this one first. Okay, so that's how we. Of course, as you download more and more chunks, you can download from one peer, or you can download multiple chunks at one time from multiple peers. So at any point in time, you can maintain multiple connections to all the peers at the same time. And you can download different chunks from different connections, right? Okay, so in terms of sending chunks, well, it's based on reciprocation. So someone is serving you in a very good manner, I should reciprocate. Okay? So Alice sent chunks to 4 neighbors currently sending her chunks at the highest speed. So I need to be a positive person. So whoever is serving me the most, I will serve him first. Okay? So this way, it's based on reciprocation. Okay? So reevaluate the top 4 the top 4 highest rate amongst all the peers in the last period of time. Those peers, you accommodate the request in terms of fetching chunks. If they ask you for a chunk, you need to give them right away. Others, you don't have to. Okay? So select the highest 4 and give them whatever they ask for.
Means who is having highest transmission rate or upload rate should be given this chunk. You mean to select this one or no? Different.
Whoever is giving you the highest rate, okay?
Upload rate.
Upload rate from their side. From their side, it's the upload rate.
Correct. Okay.
For me, it's the download rate. So whoever is giving you the fastest rate, you actually order all the peers in ascending order and select the highest 4. Okay? So these highest 4, you maintain every 10 seconds, you have to calculate or re-evaluate this highest 4. And this highest 4 will be your first peers to target when it comes to sending or uploading chunks to them. In other words, you reciprocate. Whoever is giving you good service, you give them good service. And I'm talking about, when I talk about this is not coming by chance. When you say 4, 10 seconds, things like this is the result of the experiments that they did. Okay? Because someone might say, so why 4? Why every 10 seconds? Why every 30 seconds? What? This is based on experiments. They have done lots and lots of experiments, and they have changed these parameters. And these parameters, they have found that they achieve certain type of trade-off. Okay, they maximize the efficiency of the system in terms of minimizing the distribution time, and at the same time, they minimize the possibility of missing any chunk from the group and so on. They have some criteria, and these are the parameters that they have concluded to be very good and very efficient. You have a slide loud.
Okay, why they chose 4? Because each peer can send the one chance to the other peer in one time.
Right.
Yes, they cannot. One peer, he cannot send 4 chunks for 4 peers.
They can. Why not?
They cannot.
No, they can. They can. They can. In fact, they can maintain more than 4 connections. Theoretically, you can maintain TCP connections with as many peers as you want. There's no restriction on the number of connections. Of course, there is some theoretical limitation because you cannot build like 100,000 TCP connections. I mean, it's a little bit unrealistic, but you can maintain more than 4 connections. Why not? But why 4? That's what I'm saying. Why 4? This is based on experiments.
The peers, they can have more than one chunk?
Yeah, of course. The peers, they can have more than one. Of course, absolutely. So each peer has different chunks. Could be 10, could be 20, could be 100. I don't know. When I first joined the group, I have no chunks. And I know I have no chunks. But the others, they may have chunks. I don't know. One peer may have 100 chunks. One peer may have 2-3 chunks. So the first thing that I do...
They sequence the chunks for each node.
They are sequenced, of course. They are sequenced. But you cannot restrict because we join the group at different times. So someone has been in the group for the last hour. He accumulated 100,000 chunks. I don't know. One is still joined 2 minutes ago. He has like 3-4 chunks. I don't know.
When you put the 4 at the top, are
Right.
they the 4 that uploaded the fastest rate?
Yeah, they have given me the fastest rate.
Only you, not like...
Not only me. Again, that's why I answered here. I said that when it comes to decision making, everyone makes the decision of his own. The tracker is only to maintain the IP addresses of the group, but not to restrict or dictate who should download which chunk when. This is not the job of the tracker. The tracker only maintains the IP addresses of the entire group. That's it. That's all. Okay? Type. So until now, we know that we reciprocate. We sort them in descending order every 10 seconds. So the rank of different nodes might go up or down in this rank. And we select the highest 4, and we reciprocate to this highest 4 the chunks in terms of upload. One added thing, every 30 seconds, doing this, remember, doing this might favor people with high speed, right? And the people with low speed will always starve. Starve means that these people are poor people, but that doesn't mean that we should not use them. Because the technique that we are doing so far sort of favors people with high speed, which is good, but it should also be a little bit fair to people with low speed. So those poor people, we should always kind of elevate them or help them. Okay? So this is the part that deals with that. So every 30 seconds, in addition to the highest 4, I select another 5th peer randomly.
You won't select from the 4.
No, because these 4 have high speed.
So you don't select them.
No, and I selected them,
Okay.
and I will serve them. It's good. But what about the poor people in the bottom of the list? Should I never serve them? Okay, if I do this, this means that these people will always be poor and they will never contribute to the group, and no one will send them anything. Okay? So I need to be efficient, but also I have to be fair. Okay? And actually, we call this maximum fairness. Maximum fairness. We will talk about this concept. We always try to use the most efficient, but try to elevate the poor people in order to elevate them higher, so that they will be also leveraged as part of the group. Because if I select these 4 and that's it, some people, they will never be part of the group. They are participating, they are joining, but they are never exchanging any chunks. So these poor people will always become poor people. So in order to make a good environment, we will serve, that's why we said 4. It could be 5, this parameter can change, 4, 5, 2, 3, something like that, okay? So it's like you are serving highest speed with more weight, right? But every now and then, we might as well select one poor guy, okay, and bring them in this list, and also serve them.
Like, you mean who have the bottleneck rate?
No. Here we do it randomly. So it's like you have a list of, let's say, you have peer 1. This is the order in terms of highest and lowest. Peer 2, peer 3, peer 4. Okay? So this is the order of these peers. Okay? And you have all the way to peer n. So those 4 serve. The decision is serve. Every time. Every time. I have to serve. I'm restricted to serve them. Okay? The rest, okay, I select any one of them randomly. Randomly means that at one point I can select P20. At another point, P10. P15. So every 30 seconds, I take one of this other list randomly, join the 4, and serve the 5. Why? The idea about this is that we promote the fast speed, but we also try to be fair to poor speed or lower speeds. But lower speeds, since we are selecting them randomly, this will allow us to change them every now and then. So every 30 seconds, by the way, when you generate a random number, try to do that, when you generate a random number, there is a very low chance that you select the same number twice or 3 times. Okay? The probability will be very low. So chances are this random guy will change every time. So now the people with high speed will have the privilege of P being on the list every time, right? So they will be favored. And that makes sense because I need to be efficient, right? So they will be on the list all the time. But I need to also, try to help these poor guys and select one of them every now and then. It's like serve them, but with very low weight. That's the idea. Serve them with very low weight so that they don't affect the performance of the entire system negatively. That's the idea. So I try to serve them, but in a less way.
The poor ones, you serve them. Do they upload anything to the?
They do, of course.
But why are they poor then? Because they don't upload too much things, or they don't have too much information.
No. The criteria here is the speed. Yes. They will try to download. They will try to download using the rarest first, similar to us, and they will do the same. They will rank the speeds of all the peers, and they will select the 4 and so on and so forth. They will do this. Everyone will do this exact same algorithm from their own perspective. So this technique or this algorithm will make sure that every peer is a good, positive citizen in this group. And at the same time, I'm keeping the performance of the entire group efficient, which means that I'm giving more favor to people with high speed, which makes sense. But at the same time, I'm also leveraging the low capacity of the poor users. Because if I don't do this, these users, they are joining the group, but they are never, used in anything. So in this case, it's like they are there, but they are not there. I'm not using them. I'm not leveraging them in any way.
One thing is there that download speed will always be variable in this case. Means every 30 seconds will be changing.
Yes. So every 30 seconds, chances are this poor guy will change. Why? Because I'm selecting them randomly. But the other four, deterministic. They are not based on any random thing. They are always ranked, and I'm taking the fastest. So if you have chances, if you have a fast speed, you have higher possibility of being selected. Okay, which makes sense. If you are providing efficient service, we should give you better service. If you have low speed, then we'll give you less service. But it's not that we're not giving you any service. Okay, because always selecting and ordering means that there is a high chance that some people will always be outside of this ordered list. And that's bad. We don't want to do this.
Only 4 peers. That means all the time they are serving. Yes? And even
Yes,
if
but
there's one of them that they have low speed.
But remember here, there's one thing that will change this. There's one thing that may change the fact that not every time I have the same 4. What will change it? The one who has the rarest chunk. Because the one who has the rarest chunk, I will start with him or her. And this will make me download from this guy more often because he has chunks that seems to be the rarest, which might elevate this guy to be in the highest 4. Okay? So there is a high chance that these highest 4 will change. Every 10 seconds, they will change. Okay? There is also some possibility. But if they are not changing, these people, they have very fast speed, and that's why they are being selected. That's fine. Okay? So this scheme tries to address the trade-off between the efficiency, the distribution time, and at the same time makes sure that not any of the chunks become missing from the entire group. Because if someone has only one chunk, if someone has one chunk and no other peers have this chunk, if I don't fetch it from him, he or she might exit, okay, and this chunk become missing. So our entire group becomes useless in that case, because we try to download all the file content except for one chunk. We're becoming useless. And this happens, by the way. Sometimes I download from these peer-to-peer services, whether BitTorrent or Emule or something, and the file gets downloaded up to a certain point, and then it stops.
Yeah. It's always happening.
And it stops. All the group, no one has this chunk of the file. You're stuck. So this group becomes useless. So in that case, you have to cancel and then try to re-download it some other time. Hopefully, in this next time, it will work out. Okay.
Okay.
تفضل.
If you want to share with the lowest rate,
Right.
and I have already a specific time.
A specific?
Time for 30 seconds or something like that.
Yeah, this is the 30 seconds here is periodic. I try to so
Yes.
we said every 10 seconds we update the rank. We select the highest 4 every 10 seconds. Very frequent. Huh? Every 30 seconds we select one low level, one randomly.
This time is finished, and the chunks or the file that I want to share with the that one has a low rate.
Right.
It's not complete yet, and the 30 seconds is finished.
مش مشكلتي أنا بقى مشكلته هو because his low rate.
Yes.
There is a high possibility that
Virus is-
yeah, because at the end of the day, remember, once the people who the high class people, the people with fast speed, once we finish all the chunks, we may selfishly go out.
Because they don't have any chunk to.
Yeah, and when we all go out, this poor guy might run out of chunks, and at the end of the day, he will be stuck. But what can we do for them? This scenario might happen.
So there is no backup service for something.
No, but sometimes you download all the entire file, but you select willingly, voluntarily, to stay in the group, right? But the protocol does not constrain you. That it doesn't say when you finish you have to stay for us. No, you can.
But
Once I finish, I have the right to go.
I saw in BitTorrent that you can select the upload rate and the download rate also.
Yes, true. Yes.
So if I don't want to upload at a faster rate, but the
Right.
download speed be more, then it is also possible.
It's possible, yes, but this will make you go up or down in this list. It's up to you. So it's up to you. So if you say that the upload rate is more, this will affect your download rate. Why? Because this will allow you to be elevated in the rank, and you will be high. You will be the first 4 most of the time, which means that anything that you ask for, they will give to you. Yes. So which means that your download speed will be higher. So the tool actually gives you the decision to specify. But if you specify very low upload rate, this will allow you to be always in the bottom of the list. But remember, you might select a speed which you think is low, but others are lower than you. You never know.
But the rarest first will always be in the top 4.
The rarest first?
Will always
No.
be in the
There is a technique for downloading or pulling the chunks, and there is a technique for uploading. For downloading, we select the rarest first. So this is the technique. This is what BitTorrent does. For pulling the chunks, we use the rarest first scheme. So we see which one has lowest number of occurrences, and even if we download from a low speed. Even if we download from a low speed, because we are trying again to address the trade-off between being efficient and going out of chunks. Okay. So for the download, we use rarest first. For the upload, now we have to select the fastest and reciprocate to them. Okay? So this is BitTorrent basically. So there is a terminology. There is kind of unchoked, which is the one with the highest speed, and there is intermittently choked, which is the low speed, and so on. So this terminology is used to designate the ones in the high speed or the low speed or something like this. And in the book, they explain everything using Alice and Bob, which is very common in security environment. They always use Alice and Bob and Eve for eavesdropper and so on and so forth. So you can read it as a story if you like. Okay, but I hope the concept itself is clear. A tick for tack is like we reciprocate. You give me good service, I give you tick for tack. This is what it means. You give me good service, I give you good service. Okay, so this is what it means. Okay. Yeah, so we'll get to distributed hash table next time, inshallah, because it's a totally new topic. Okay, so we'll stop here.